All right, welcome back to Zed Decoded. I'm here with Nathan and Antonio. Say hi, fellas.
Hey.
Hey everybody, welcome to another exciting edition.
All right, so the story in this case is about property-based testing, no-frills property-based testing, and the story actually starts not with Zed, but with the first editor that you guys collaborated on, which was Adam, the one that spun off Electron. Nathan, you want to just tell us sort of like the motivation and what experiences in Adam led you to decide that we needed to get some randomized testing into Zed?
Yeah, I mean, when I was working on Atom, I was obviously much younger and had a lot more to learn. And I had heard of property testing as some Haskell concept, like out in the distance. But I was writing a text editor in JavaScript, so I had bigger problems. uh, but so as the complexity of what we were building from a data structure and algorithm perspective was sort of forced to ramp up by our need to improve performance, right? Like when we started, we just went with really basic approaches, but they didn't perform well. But as we started introducing trees and more complex, crazy stuff to try to make this thing go faster, we started getting errors, um, you know, coming in from users in the field. And it became extremely difficult to analyze like how the heck we got into these states. And so the unit tests that I had been writing were just no longer covering enough of the possible edge cases of these more complex structures that sometimes involve randomness themselves, et cetera. And so finally, out of desperation and pain, I was just like, let me literally just take some of these data structures that are, throwing stack traces and just like test the living crap out of them by bombarding them with every possible combination that a user could potentially do. Essentially, simulating the chaos that was out there in the real world that was like plaguing me and my stack traces in production. And so the first day I set that up, and yeah, I got some of the exceptions to happen, and then I was like, oh, shoot, I have a problem. I don't know how to make that happen again. So then, shortly thereafter, coming up with the idea like, why don't I fix the seed of the random number generator? I think Antonio, you were maybe there with me that day, and thus began our sort of accidental foray into this sort of poor man's approach to property testing. Definitely, JavaScript didn't have any magical quick check thing. And so anyway, naturally, when we went to build Zed and apply everything we learned creating Atom, um, we obviously took a lot of lessons about data structures and algorithms and what language is appropriate to use to write an editor and what isn't. But another thing that we took with us were another thing that we took with us were some of our lessons about how to test these complex data structures effectively. And so, yeah, that's the story of how we got here.
Yeah, so it sounds like, I mean, it's cool that this was a response to a problem. The problem being that, users are using the editor in so many chaotic ways that it's just really difficult to try to predict and enumerate all the different things that might lead to a crash or something going wrong. And then the randomized testing was a good way to reproduce those things just by throwing random data at it. And then, like you said, then the problem becomes how do you reproduce it? And then fixing the random seed is a way to do that. I'm curious, like having written one of these myself back for like Elm test, the way that I did that was basically threading the seed that was coming in from the command line all the way through every single generator of every single thing. Was that something that you guys did by hand, or was it that you sort of set up your own little framework for like threading the seed through and making sure that there was no, going back to the system random number generator and like bypassing the seed?
I mean, it's been a long time since the Atom days, so I don't quite remember, but we can talk about what we do in Rust today, which, might be a good segue. Yeah, I don't know.
Yeah,
But
let's
basically, yeah,
transition.
fixing an RNG. Yeah.
Yeah. So here's a test that we wrote in Rust. It's actually like a little bit some of the complexity of the RNG is hidden behind this macro, and maybe it's worth kind of getting into it. But yeah, this is kind of like the way that this is threaded through is like by this macro right now. Like the RNG is given to us in this test. But yeah, if we kind of zoom in, yeah, the idea is that in this macro at some point there is a way where like we sort of fix the seed. We look at the seed from the environment variables, like seed from U64, seed. Okay, this code has changed a bit since last time. But yeah, the thought is that like you can sort of pass, you can fix the seed via via an environment variable. And so yeah, the idea is that by default, if you don't specify any environment variable, like we will start, I think we'll just start at 0 and we'll go from 0 to 100. And that's literally like the U64 that we pass into the random number generator. But obviously you can also sort of manipulate that, change that and say, okay, I want to start at seed X and run, a million iterations, which is, something that we've done for some of these data structures.
So maybe it would make sense before we zoom in on too many more like implementation details of the testing framework, just to walk through one of these.
Right. Yeah, so
stuff.
This is like a test for one of the core data structures in Zed, which is the text buffer. And, this is what basically lets us manipulate text efficiently in, logarithmic time. And so you can notice here, like, we start with this variable operations. This is kind of the amount of random mutations we want to perform to this buffer. And notice how like we say, okay, we'll start with a reference string, like literally like we take a bunch of random characters and like collect them into a string. And then we sort of instantiate the buffer, which is like the data structure under test with that reference string. And then we sort of like, subject this data structure to all these like operations that we decided before. And like, yeah, for each operation we say, okay, now we want to randomly edit this buffer. And so I can get into like, yeah, what happens inside of randomly edit. But the idea is that, we get back a bunch of edits. So like we edited the buffer and then these edits we want to also apply to the reference string. And so, one of the properties that we assert on is that the text of the buffer should be the same as the reference string. And, this might seem like a simple test, but you'd be surprised to see like, how many iterations it took to make it pass.
And what it hinges on is like, if you go to the implementation of replace range on, well, it's in the standard library, right? But like,
right.
Ultimately this is not a very efficient thing to run, right?
Mm-hmm.
Like we wouldn't want to back an actual text editor with a string because if you load a big file and you're replacing ranges and moving memory around, like that's going to be super slow. Mm-hmm. And so it's very simple. The mental model is very clear, but it's not production ready. And so that's what we can do. We can kind of stand up this simpler model that doesn't perform next to the more performant data structure and make sure they match.
And this is one of those sort of classic techniques in property-based testing is it's like, how do you assert the property? Like the property that we want, because we want to know that it's like quote unquote correct, but how do you know that it's correct without just re-implementing the whole thing that you just did? And therefore it's just testing that the implementation is the implementation. And the answer is, well, you have a known correct implementation that doesn't have the performance characteristics you want. And then you can assert, does my high performance alternative to this known correct thing give the same answers as the slower one that's correct?
And you can also assert on other kinds of invariants, which we do all the time as well.
I mean, here's an example of that. Yeah, like, and these are more kind of like internal. Obviously, these are not as clear as like, we're asserting on a piece of text, but like we can sort of have this contract with the data structure that so long as these invariants are like maintained from iteration, from operation to operation, there's at least some sanity in the data structure, and like we sort of can build upon it.
Yeah, and then you can also do things like trying to verify side effects. Like, for example, if you just like replay the same thing multiple times, does it get the same answer, or does the answer change each time you replay the operation? Things like that.
Right. Yeah. So I mean, and this. So yeah, here we assert on the text, right? Like here we assert on the invariants, and but we can also assert on all kinds of APIs. I mean, you can see here like 30% of the time we capture a snapshot of the buffer, right? And this is something that like we need to do a lot in Zed, where like we want to basically diff potentially two like versions of the buffer and produce edits for those two versions. And so here like we sort of snapshot the buffer at a certain point in time, and then ensure that like if we sort of grab all the edits that happened since that version and apply them, we end all the way back to we end to the current string, right? Like all the edits lead to the current string that's currently sort of stored in the reference
So we're
tree.
actually kind of testing multiple properties of this thing and potentially multiple even different behaviors that it supports, kind of all in the framework of one randomized mutation test. And like, yeah, so everybody's heard of test-driven development, TDD, right? And yeah, a few years ago, people were trying to claim this term BDD, but I think we should reclaim BDD as blood-driven development. Because especially in the early days of Zed, like in our first year when our seed investor was like, where the hell is this editor that I supposedly invested in? We lost my headphone. We spent our days just like bashing our brains against these randomized tests, right? You're building these data structures that are very nuanced. And then your goal is to just like run hundreds of thousands of iterations in some cases without hitting a problem. And it's just like, yeah, you want to believe, oh, we got to 10,000,
Maybe this
20,000.
time.
Yeah, exactly. And so it's really just like elbow grease. But the cool thing is like, if you can make one of these tests you have so much confidence in what you've built.
And I feel like oftentimes what it does, like going through these iterations, is like really help you build a very strong mental model of the data. Like, I think when you start building one of these structures, like you think you know what you're doing, and for the most part maybe you do, but like not quite, and sort of like all these like poking at the problem space, and like with this random number generator, like really helps you kind of form a better and better hypothesis of the problem you're trying to solve.
Right. Like a thing that people often say about TDD is that in the course of writing the tests before writing the implementation, it helps you understand what are the characteristics of the implementation. You can say the same thing about this, where it's like you have these properties, these invariants that are supposed to hold about it. And then when you're going to build the implementation, you now have those, more in mind, or even as you're revising the implementation. I also liked your point about how many iterations it takes to find one of these things or to find a problem after you've sort of refined it and gotten rid of the low-hanging fruit. I think that really reinforces like the concrete need for the seed. Because you imagine if you had to leave this thing running for an hour before it finally found the problem, you don't want to have to be like, okay, I think I fixed it. And then you rerun it for an hour and you're like, did I fix it? Or did it just not come up in the hour this time? You don't really know. But if you have the seed, then you're like, yeah, no, I can just exactly run those combination of inputs and see it work again.
And one thing that we do is like we actually, all of these seed, we always start from the same seed usually. Like we start from 0 all the way to n. So chances are that like, we'll hit the same seed again and like try again the same set of operations. And so, if we get past that seed that previously failed, you can be reasonably confident that things work. Unless, I guess, you change the test because maybe you made a wrong assumption, so now everything is changed again because like the RNG sequence is different.
And I know there are now. I know there's like frameworks now that let you sort of maybe shrink the search space or do some more intelligent things than some of the brute force tests that currently exist in Zed's code base. I'm not sure when we wrote a lot of those that any such frameworks actually existed. But it could potentially be improved in that way.
100%. There's like other things that I think like I read this in a blog post from Matt Glad, the creator of Rust Analyzer, and I think it's a really cool idea of using those things called fuzzers, where like they actually profile the branches that your code is taking, and sort of they try to establish this relationship between this stream of random bytes that they generate and branches in the assembly code that actually are taken. And so they, the fuzzer kind of tries to like, change the input stream such that like you take all the branches. So I think that's a cool thing that we could probably do. But yeah, we haven't gotten around. I don't know. There's so much to do.
but one really cool takeaway from this whole thing is in every project that I've ever worked on with any kind of IO complexity, I always had the problem of flaky tests on CI. I mean, our good friend Jason Rudolph even spun up a whole company around that, right? To just monitor flaky builds and help people firefight that. And as a reaction to that, and kind of derived from having good experience, like subjecting data structures to this blast furnace, we actually took this randomized testing approach to the limit with that. And I actually think it would be worth showing one of these integration tests that we wrote, right? We're a monoglot shop. We have a little TypeScript on our website, but like otherwise we're Rust, right? Backends in Rust, front ends in Rust. It's all in this mono repo actually. And so we're able to write these tests that essentially simulate all of the potential sort of network interactions, file system interactions, any IO or sources of randomization, we're actually able to simulate with our own scheduler that we wrote in Rust, right, to kind of exercise all the possible timings. So yeah, Antonio, take it away.
Yeah. So there's two pieces to what Nathan is talking about. One is basically being monoglot, like being able to write these integration tests where like we can literally, we have this enum where like, we'll generate at random a server operation, right? Like we're adding a connection, we're removing a connection, we're bouncing a connection, or restarting a server, right? Or, we can generate a client operation. Where's this? I guess stored operation is T. Sorry, let me find it. T operation. I guess this is generic over the client operations. But yeah, point being that like you can have like this swarm of clients kind of collaborating with each other. And so like here in run randomized test, this is kind of like the little framework that we have for running these randomized tests. This is kind of more complicated than the other one we just saw, because like here we can actually save one of these traces of operations, and we actually implemented our own shrinking. Like we have this script that kind of takes a JSON of operations and kind of tries to reduce it, because sometimes you need 200 operations to kind of come up with a problem, a failure. Yeah, so this is like one side of it, right? Like the sort of the being able to generate like server and client side operations. On top of this, one thing you'll notice is that here we're using awaits, right? Like when we start a server, we are waiting, and when we are creating one of these plans, we are waiting. Now, the cool thing about the way this is structured is that given that Rust lets us control how futures are, scheduled, we even there we have the chance of having a random number generator with a fixed seed that lets us scramble the order of like these futures always in a random way, but with a seed, so we can always fix that order. And that gives us the confidence that if we have two things happen, two tasks that are spawned at the same time, we can kind of randomize the order in which these two things kind of interact with each other. And so in the case of clients, it's been a while since I've looked at this one particular test, but each client is basically like in its own task, and it's doing, it's performing operations on its own. And so not only it's, we're randomly generating operations using this RNG, we're also scrambling the order of execution of those operations, which gives us this really like rich sort of trace of possible executions of a program that we can then have assertions on.
And not only scrambling the order of the operations, but literally scrambling the order of the individual kind of handling of IO, right? Mm-hmm. Like the poll completion callback or whatever of the IO coming in. Right. Can always happen in these random orders, and we're actually exercising all possible orders.
One cool thing that we do is, in order to do this, you need to be able to, have fakes for all of your IO, because as soon as you introduce non-determinism that you don't control, like say that we actually use the real file system, for example, to write and read files, then it's very hard to make these tests reproducible. But one thing you'll notice in the Zed code base, if you look at it, is that whenever we can have these sources of randomness, we usually have a trait that kind of abstracts over them. So in this case, like the FS trait, we have a real FS struct, right? That actually uses I think it uses small to perform I/O. And so this will be the actual one that mutates the file system. But we also have a fake file system that is all implemented in memory. So we have this fake FS state, which is a tiny, a modest implementation of a file system in memory. But the cool thing about it is that anytime you call one of those functions that are in the trait, for example, let's just say we want to do write, we have this method here called simulate random delay. And all that this does is it sort of talks to the executor and kind of, this is hidden different layers of abstraction in GPUI, but like, simulate random delay. At the end of the day, all it does is it takes that random number generator, which, again, has a fixed seed, and decides, okay, I'm going to yield control back to the executor, between 0 and 10 times, right? And so what that does, automatically is that we sort of simulate the amount of ticks, so to speak, that it would take for an IO operation to complete. And so this lets you kind of, if you have, like I said earlier, two tasks that are kind of spawned at the same time. Yeah. Go ahead, Nathan. Yeah.
Or that are racing. Yeah.
Exactly. Yeah. You can sort of simulate that one finishes before the other, or, the opposite, right? And so, yeah, I think this is a really, really cool technique.
And even things like really extreme network delays, right? Where you have let's say that there's somebody who's on a really bad connection and like a 3-person collaboration. 2 of the people are going back and forth making lots of edits, and the third person's edits are really delayed. That's so hard to simulate in a real world scenario with a real network IO. But when you control the entire network stack and can simulate anything you want, that just becomes one more scenario for the random number generator to come up with.
Totally. And this is kind of the crucial primitive that lets us kind of wire a client and a server, that lets us simulate that thing Nathan was alluding to earlier, of we have clients and server all wired up in this one giant integration test. And, we can kind of fake this in memory connection between, these two, a client and a server. And you'll notice here that we sort of abstract over, again, a sink and a stream. So a channel can kind of produce data and receive data. And once again, here's our friend simulate random delay. So anytime you send, you can, you'll be subjected to a random delay. And anytime you read, you'll be subjected to a random delay. And in the process, we also have we have ways to kind of kill the connection and simulate all kinds of other stuff. But yeah, this kind of lets us introduce kind of asynchrony in an otherwise synchronous process, because it's all in memory.
And it's incredible because our CI suite, for the large part, outside of some very focused integration tests on kind of the real FS, for example, and other particular scenarios, our CI suite is deterministic. So we're able to test non-determinism deterministically, which is anyone who's ever had to wait on a flaky CI build that fails due to a flaky test is really important to maintaining velocity. I have an idea. This is a little crazy, but what if we pivot into talking about the randomized scheduler? It's pretty nerdy. It's in the weeds of async Rust, but I don't know, async Rust, for anybody that encounters it, you're like, what is going on here? For me, at least, the learning curve was intense when I first encountered async Rust. But it enables some really cool things that you just can't do in other languages. Would it make sense to look at that a little bit? Or I don't, yeah. Or is that,
let's get nerdy. Right. Let's do it.
Okay.
I'm down. Yeah. So, I mean, I think that
should we explain, set the context though, right? Of how async Rust works? Oh, you can do that, but yeah, okay.
I'll do it. So yeah, basically, the big concept in Rust is this idea of a future. A future is basically this very simple trait, actually, that has an output. So it's something that at some point will return some output, but maybe not right away. And so you need to continuously poll it, right? So you would implement future for any struct that you want, and you would need to poll it. And this poll enum is basically has 2 variants, ready and pending. So if the future is not ready yet, it will return pending. And as soon as it's ready, it will return ready. And I think it's a violation of the contract to call poll again after it returned.
So can I
ready.
jump in here? Like if you're familiar in JavaScript with a promise, for example, right? This trait, this interface that you need to implement in order to can we go back to that future trait?
Yeah. Mm-hmm.
This is basically like your ticket to basically implementing your own implementation of promise. And you do that by saying, when this thing is ready to make more progress, here's what I want to do, right? That is by implementing this poll method, right? Is sort of make a little bit more progress on this future thing that's not yet ready, right?
And most of the time you don't even notice that this is happening because, and this is something that a lot of languages have nowadays, but yeah, Rust has it too, which is being able to create an async function. So an async function, what it'll do is it will generate, a struct under the hood, right? That implements that future for you. And like, basically you can have await points and, it'll create this like, small, or maybe not small, state machine that, will drive that poll implementation that Nathan was
right. So the compiler, when you use this cool async fn syntax, will implement that trait for you, right? And like just like it auto implements other traits.
Right.
Back in the day, you at the very beginning, you had to literally implement poll yourself. Like they didn't even have the async syntactic sugar.
I remember that.
And there are still times where it makes sense to do that, right? But anyway, with that background set, I think it now makes a little more sense to contextualize the scheduler, which holds all these futures and is basically calling this poll method so that they can make a little more progress.
Right. One little extra piece of information is that one thing that a future can and should actually do is, notice here that there's this parameter called context. The future has a chance to kind of capture a waker, what's called a waker, and kind of store it somewhere and like use it later so that the executor, to notify the executor and tell it, hey, this future, or somewhere in the stack of futures, because I guess futures can stack, there's a future that's ready to be polled again, right? And so this lets you implement things like an event loop essentially.
Right. So if you were hooking into an event loop, and I think this is how like Tokyo works, for example, right? It basically is gonna, register that waker on like epoll or whatever the underlying like async implementation of the operating system is. I'm probably out of date with that. Is it something better now?
No, I think it's probably there used to be this thing called Mio. I think they still use that.
MIO.
Yeah.
Right.
MIO, yeah. I have the worst pronunciation of all the libraries out there.
Mio. Mio. I like Mio.
Okay, Mio. Yeah.
It sounds Italian. Okay. Mio.
Mio. Yeah. Mio, which means mine. Okay. But anyway,
Mio amico Antonio.
Mio amico Antonio. But yeah, so like this is kind of, we mentioned Tokyo, right? So Tokyo would have this like, fancy way of kind of implementing, an event loop. For us, one thing that we showed earlier was that GPUI test macro, right? And notice like usually in Rust, you're not really able to create a test with an async function. Actually, what you do is like, this is how you create a test in Rust. It's like test foo, and it's synchronous, right? But yeah, so what GPUI test does is basically like it will sort of let you create this function that returns a future, and what it'll do is it'll call block internal on the executor. I guess it actually calls block on, but like it will at some point call block internal, and this is the thing that this is our implementation basically of the executor. So maybe we can drill a little bit in this function if you want.
Yeah.
So like basically notice how essentially like we're blocking on a future, right? And so the outermost future we would be blocking on is that async fn test function that we saw earlier. And so the idea is that you can create one of those wakers that I talked about, right? Like where we can sort of basically here you can just create a waker with a function. All we're doing here is like remembering that there was a future that has been woken up, and we create a context. So you can always create a context from a waker, and then the poll loop begins. So we start by polling this future, right? And if it's ready, we're good, right? Like we don't have to block anymore. We can return the result. However, if we're pending, and I guess I'm going to gloss over on the max ticks because that's another thing that we do. But if it's pending, it means that this future, right, is blocked on something else, right, that needs to make progress, right? Like this future cannot make progress unless there's anything else, there's something else in the system that also makes progress. Now, what we do is we have, given that we control all the sources of I/O and we control how tasks are spawned, and spawning is just a way of kind of creating long-lived, sort of yielding control of the polling to the executor, telling the executor, hey, here's a future, poll it for me to completion. What we can do is say, like, okay, if this future is pending, we ask this dispatcher, and the dispatcher is like I said, this kind of test-only implementation of our own executor. And we ask the dispatcher to tick, right? What does tick do? It checks that there isn't, it tries to make progress in other, areas of the executor, like other tasks that.
Right, like we're blocking on the outer future, but that outer future may have spawned other futures, right? And all those spawned futures are registered on the scheduler as state. And so then when we tick the scheduler, it needs to pick one of those futures and try to make progress on it.
Right. And so there's like a variety of kind of async things that like this future might be blocked on. One of them is a delayed runnable. And we use this thing called async task. But yeah, like a runnable is just a future a task that's ready to be polled again. But yeah, the idea is that, we could make progress on a timer. This is kind of what represents timers in our executor. Or we have this notion of a foreground future, right? Where like, we can say, okay, like here's like the number of foreground futures that we have. Here's the number of tasks that we have. Here's the number of background tasks that we have. And it's somewhere in here, we say, okay, now let's grab one of those things at random and kind of make progress on those, right? Like poll it once and see if, it makes progress. And so, as we do that, what's going to happen is that like, how this future just returned pending. Well, if after we tick, right, the awoken Boolean, right, that was set by the waker hasn't been set back to true, meaning like no progress happened, right? Like this future returned pending, and like nothing in the system caused us to wake up this future. If parking is not allowed, and this is like other stuff that happens here, but like if parking is not allowed, like we panic, like we fail the test, because it means that this future will never complete. Like there's no way in the system to make more progress.
Let me try to like
unpack it.
Sum that up a bit. Like if no futures are able to make progress, the test fails, right? Because we're going to hang forever, and we kind of know that we know deterministically. We don't need to wait for the test to hang. They're all saying, "I'm pending," and then we have this loophole where we allow parking, which is basically our like. Sometimes we need a loophole where we can actually do I/O, right? I think it's basically why we have that. And then we can also like run until park. We can tell the scheduler, drive forward until nothing's ready to make progress, right?
And that's a really cool like way of. I don't know if you've ever done this, but I remember like remember writing those like integration tests for like web pages where like you would assert on a certain piece of text not being present in the web page, kind of like negative tests. Right. What this allows you to do is kind of say, hey, executor, run until parked. Like, make sure that nothing, can make any more forward progress. Well, now you can write that negative assertion, right? Because you know that, like, it's not just a flake, right? That, that piece of text wasn't present. Like, there's no way that piece of text could ever appear in the web page. I don't know if that,
Right. So it's partly that it eliminates race conditions in the test itself, where you're not like, oh, did this test only pass because I got lucky? Like, was it a false positive? That's not a thing anymore. But another sort of unsung benefit of this approach is the performance of the tests. Because if you're just like writing to a temp file instead of like mocking out your file system and using this, one of the things that can happen is if the test gets into this stuck state, how do you detect that? Well, often you just write a timeout around it and say like, well, if it takes longer than this many seconds, it's probably stuck, so fail the test. But of course, then what happens is you get your first positive one of those. You're like, oh, well, we got to bump up the timeout because obviously,
right.
that right.
Right,
And
right.
before you know it, now you got your CI suite, and it's like, oh, there's a failed test. I'll find out about that in half an hour.
Right.
It's so much better to be able to have this completely deterministic thing where you have no concern about false positives or false negatives because it's totally deterministic, and it runs as fast as possible, even though it's potentially simulating things that would take a long time of like physical seconds to reproduce if you were doing them manually in real life.
Right, and this is all the fruit of like Rust's hardcore approach to like, abstraction, basically, like just giving you this deep control and zero cost abstractions and the control you need to make those abstractions zero cost. It all gives this like programmability to the underlying runtime, basically, that just you don't find in other languages.
And I think another cool thing to note here is that, on the one hand, like you were saying earlier, maybe there are some off the shelf crates that would do a lot of this stuff for us, but it is pretty cool that we have the tools to just do it ourselves anyway. Like, it's not required that you go and take something off the shelf. It's not so complicated that mere mortals cannot create their own randomized testing setup. It's like, yeah, actually anyone can do it as long as you're sufficiently motivated to say, like, we want these characteristics out of our tests. Let's go and build the infrastructure to make it happen.
Yeah.
Right.
Having said that, if anyone does know of any really cool tools that have come out, maybe in the past 4 years or so, that maybe should be on our radar, feel free to drop us a comment. We can maybe take a look and, never hurts to upgrade your setup if it turns out there is something that we could benefit from.
Yeah.
And don't forget to like and subscribe.
Okay. Okay.
Nice.
If we reach 30,000 likes, what are we gonna do? I don't know. It's usually the call to action.
Yeah. All right, cool. Well, we covered a lot of ground. Is there any other aspect of this that we should make sure to talk about before we wrap up?
I don't know, probably, yeah. But I mean, one cool thing, you talked about performance. One thing I want to say is that sometimes when we need to run like a gazillion iterations, we'll run these tests in release mode. Like, we'll literally like compile a optimized binary to like run a lot of iterations. And run them as fast as we can because sometimes the millionth seed is the one that's gonna fail and you want to find out as soon as you can.
Right. Usually waiting for a full release build is not a time savings, but if the iteration count gets high enough, it can pay for itself. Pro tip.
Yeah, so if Zed ever panics, and I don't think our panic count is 0 right now, it's not for lack of extreme trying. And my overall sense is if you ever want to build a system backed by a data structure of any complexity, don't unit test it, property test it, or do both. Probably do both. That's my main takeaway from my entire career working on editors and working on applications that rest on complicated things that need to perform. Your edge cases are, if it can happen, it will. So why not have it happen in your little petri dish where you can control and understand it? Don't wait for it to happen to your users.
Beautiful.
Love it.
All right. Well, on that note, thanks so much, guys. This has been a really interesting deep dive into how we do no-frills property testing in Zed, and hope everybody out there learned something from it. Thanks so much.
Thanks for watching, everybody. Bye.